Ci siamo? Great. So, welcome back. Lesson 7, and now we go to real physics. I hope now with the next one, but I think this one. We're doing quantum gravity, quantum. So what is the main discovery, physical discovery with quantum mechanics? Quantum mechanics is a general discovery about nature. It's more than one thing. It's probability, it's the fact that there are interactions. But the key one is discreteness. So that's seldom said, but quantum theory, its key discovery about the existence of some kind of discreteness, a very peculiar kind of discreteness in nature. And in fact, this is the core of quantum theory. That's how it was found at the beginning, right? Both in the paper by Planck, where we had this discrete quanta for the black body radiation, in the paper by Einstein. 5 years later, for the photons, he realized that he invented the photons, so he discovered that the magnetic field has photons. And then the discreteness of the atomic spectra, discreteness of angular momentum. In quantum field theory, the field, the classical field, when you look at its quantum properties in the small, so to say, you see the particles, which are the quanta of the field, so on and so forth. So discreteness is a very, very general thing. You can think that in phase space, in the phase space of a classical theory, which is the possible sort of configuration of the system, you cannot localize the system better than a Planck-sized cell. So if you have a region of phase space, you know the system is there, and you measure a variable that distinguishes the point in this region without sort of changing the fact that the system in that region, then this variable is necessarily discrete, because if it was continuous, it would allow you to localize in phase space better than a Planck cell. So in particular, any variable that separates finite regions in phase space is discrete. Like energy in the two-dimensional phase space of harmonic oscillator, the equal surface energy are ellipses. And so between there is a finite region, this is discrete. So this is the key point about quantum mechanics. Quantum mechanics is, first of all, the discovery of some discreteness in nature. And that's, I think, it has to be stressed over and over and over.
There's something I truly understand. It is true, for instance, as you said, the eigenvalues, for instance, are discrete, but we can perfectly have formulation in terms of Schrödinger formulation, where we have wave functions which are objective, which are not discrete at all.
Yeah, there is a.
Continuously.
Yeah. I was reading a beautiful series of lectures by Schrödinger that he gave in Dublin in the 50s. And I stumbled on something that Schrödinger writes. It's very beautiful. He says, the creators of wave mechanics, which is himself, who else, hoped originally to have found a way to reinterpret discreteness in terms of a continuous wave function, but they were misled because they only moved the discreteness from the continuous evolution of the wave functions to the measurement. If you want, if you have a particle, the wave function spread continuously. We put the particle in a point, let it evolve with the Schrödinger equation, becomes a wave, and then when it interacts with the screen, boom, it just becomes a point here. So the initial hope that you could resolve entirely the discreteness of Bohr, of Planck, of Einstein in terms of wave function, it's not only dead because it just leads to the measurement problem, but it's worse, it's misleading. It hides the problem under the table, and then everybody's confused about measurement. So discreteness is a core of the theory. Cannot be avoided. It's not only it cannot be avoided. It's what the theory is telling us about nature. Of course, it's a funny kind of discreteness, right? It's not classical discreteness because of all the way quantum mechanics works. It's related to probability. It's related to the interaction, but it's definitely there. And the easiest manifestation of discreteness is that some of the variables. Remember, classical theory of quantum theory describes a system in terms of variables. Some of the variables just take only discrete values. It's a fact. The angular momentum only have discrete values. The energy of a harmonic oscillator have discrete variables. The energy of a wave of a field of a given frequency only have discrete values. That's how you build Fock space, and so on and so forth. So discreteness is core. The electromagnetic field is made by photons. The electron, the atoms have discrete energy levels. And if you want, is the reason for which atoms are stable, because there is a minimum energy level. The electron cannot spiral down more. It would concentrate more in phase space. It's a reason for which there is no ultraviolet black body catastrophe. So why, given thermodynamics, why energy doesn't thermalizes going to arbitrary high frequencies? That's what classical mechanics tell that, right? But that's what people were worried at the end of the 19th century, and Planck was trying to figure out why the black body spectrum goes down on both high frequency. Because when the frequency is very high, you have the vacuum state, and the first excited state, because of discreteness, it requires a lot of energy. So you cannot fill it with available energy. So you just have that's why you get the Planck spectrum, right? Instead of the classical thing that would explode the diverger high. So energy, discreteness is all over, is what allows thermodynamics equilibrium for fields, is what allows stability of atoms, and of course it's also here, and what it will manifest itself in the finiteness of the black hole entropy and things like that. How do you concretely compute discreteness in quantum mechanics? Well, you all know we have a non-commutative algebra, as I said, and the variables in the algebra, the observable in the algebra, have a spectrum. Spectrum can be defined abstractly, but we're working with Hilbert space, so the simplest way to define a spectrum is just the eigenvalue equation. So these are the eigenvalues, this is the eigenvector, and somehow the key interpretational postulate of quantum mechanics is that the variables are described by this algebra element, and the value that the variable can take are only the spectral, the value in its spectrum. So a spectrum can be continuous for some variables, but all the variables that have a discrete spectrum, not all values of variables are possible, only some which are in the spectrum. This is something you know very well from elementary quantum mechanics. This is how you compute the energy level of an atom, or the value of Lz, and so on and so forth. Good, so this was just a quick reminder. We have a theory, at least we have the kinematic of the theory given this morning. Let's do this. So the theory we have is the Hilbert space, actually the gauge non-invariant Hilbert space H tilde gamma is SU2 to the L. The gauge invariant Hilbert space is the gauge invariant things, and sitting inside here, SU2 to the L over SU2 to the N with gamma. Let's just define this. So this is the Hilbert space where these things live, and we have operators, and we have operators sitting here, which are the left invariant vector fields associated to the links, and which are not defined on the gauge invariant Hilbert space. Out of this, we have constructed these three operators here. The A square, we can call it the V square, and the GLL prime, which are well defined here. We have given, or at least I have given a first sketchy interpretation of that geometrically, namely this, or more precisely this multiplied by h bar g, and then a number, is the, you can think of as a vector normal to a face of a tetrahedron in a triangulation of space-time. So space-time, you're not describing its geometry, but you're describing its approximate geometry with a triangulation of flat tetrahedra. For each face of a flat tetrahedron, you have a vector E associated to this triangle, and this becomes an operator in the quantum theory, which is h bar g L associated to the link, where the link is the link of the graph dual to the triangulation with this sits. So remember, the node are the tetrahedron, the link here are associated to the triangles. So to each link here, there is an operator L, it's oriented, it's sort of sitting here, and its interpretation is the normal to that with a length proportional to the area. So this A thing here, it's the square of its length. So A is the area, AL is the area of the triangle, and VL is the volume of the tetrahedron. What about these things? I didn't mention these things. Well, this is a scalar product of two L's, one here and one here. So this is also gauge invariant, right? Because they both transform under rotations here, but a scalar product is gauge invariant. So what is it? Well, it's very simple. You have the normal here, and you take the scalar product. So what do you get? You get the area of this, and the cosine of the dihedral angle between the two, which is essentially the dihedral angle between these two, between these two planes here, or pi minus it, whatever. I mean, the proper thing, right? So this is an operator that reads the angle of the tetrahedron. Obviously, if you have the area, the volume, all the angles, you have the full geometry of the tetrahedron. If you have the full geometry of all the tetrahedra, in principle, you can reconstruct the geometry of the space up to that approximation. And of course, classically, this is a truncation, but any given geometry, you can approximate it arbitrarily well by taking the tetrahedra as small. So if you have a given geometry here, you approximate with 7 big tetrahedra, you have a rough representation of the geometry. If you approximate it with 7 million little tetrahedra, you have a very, very good reconstruction of the geometry. So you can go arbitrarily fine with more and more tetrahedra, and you get a better classical description of the geometry, just in terms of these quantities here for all of them. Good. So now that we have, yes.
For each node, we got 4 vectors for L.
Yeah. Yes.
But we only need 3 vectors to define the total geometry of the tetrahedron, like angular momentum.
That's right. That's right. That's right. So for each, let's do the counting here. For each node, we have 3 vectors, which is each one has 3 components, so it's 9 numbers, right? But of course, I've chosen an arbitrary basis here, so this is invariant under SO3. So what matters is only the scalar product, the invariant part. So 3 This is number up to rotations. So the rotation group is three-dimensional. So the gauge invariant part is 9 minus 3 is 6. Okay? And 6 is exactly the degrees of freedom of the geometry of that. If you want is 1, 2, 3, 4, 5, 6. If you fix the length, 6 length, you can compute everything else. Right? So the space of the tetrahedra, namely the space of the possible shapes of a flat tetrahedron, is 6-dimensional. Okay? And it's completely captured either by the 6 length or by 3 vectors, each one having 3 components, 9 up to common rotations. Same thing. Now, somebody could say, well, there are 4 vectors. Yes, but there is this equation here. So the fourth one, they're not independent. So if you want, you start from 12 minus 3, 9, minus 3, 6, which is what we have. This is important. Okay? Good. In fact, this is very important. So now I'm going to do a calculation, essentially, and solve the eigenvalue equation for the area and for the volume entirely. Okay? And compute the spectrum, both of them. In fact, one explicit, the other one implicit. And you'll see what the spectrum is, and I write explicitly the eigenstates of them. So in a sense, it's an exercise. I could give you an exercise. Now, everything is well defined here. There's nothing else. The rest is just a good mathematician. So I'm going to do it. And in a sense, I've already done it. That's why I did the mathematical part first, because the mathematical part, you can think it as a solution of that problem. And let me show why. I gave you in a single L2 of SU2. I said there is an orthonormal basis which is given by these things here, djmn of H, the Wigner matrices, which are explicitly known. And this, for a fixed jmn, this is an element here, so I can write it as the abstract vector g, the abstract element of the Hilbert space in the basis H. Okay? This is H, sorry for my horrible writing, jmn. Yeah. I'm going to go back to that. Now, here we have this space here, which is not L2, SU2, SU2 to the L. So we have L copies of that. So a basis, so a possible basis in L2, SU2 to the L, you have one of these per each HL. So the basis is given by D, J1, M1, N1, HL1, DJ, big L, ML, NL, HL, and this is HL, and the quantum numbers that label the basis is JL, ML, and NL. Okay? So this, I know exactly how to write this state. These are just a product of Wigner matrices. Abstractly, what I'm doing, I'm writing this as a sum over all possible. Let's do it slowly. So this is a tensor product over L of this. And this, we wrote it as the sum over J of Hj tensor Hj, which is to say that in any L I have a basis which is labeled by J, an M here, and an M here. J, M, and N. Right? Remember that this spaces Hj have a basis Jm. M going from, so a basis M. And J just label, it's a label that reminds you of which representation you are. Now, this I can rewrite exchanging the sum with the product as the sum of, I have one J for each L, so I can just put a little L here just to be, that's what I did here. As a sum of the possible JL, so the assignment of a spin to each link of the tensor product over L of this thing here, HJL tensor HJL. Now comes the interesting part. Think about the structure of this. Take a node. I said they're four-valent, so my drawing has. Consider a link. This is the link L, and to this link there is this matrices added with one index here and one index here. So this is a space where this index lives, this is a space where this index lives. Now, when you act with gauge transformations, the gauge transformation here act on one index, the gauge transformation here act on the other index, obviously. Because when you multiply here by a group element on the left, this is a representation. You get the representation acting on the left, on the right, on the right. So if you act on the left, you act on this index. If you act on the right, you act on this index. So the gauge invariants on the source node act here. The gauge invariants on the target node act there. So these two indices actually sit naturally, say for this link here, one here and one there. One transforms under the gauge transformation here, the other transform under the gauge transformation there. Right? You following? So it's a great idea. All these Hilbert spaces, which are a couple of Hilbert spaces on all the links, to regroup them by node. So take the Hilbert spaces, the four Hilbert spaces here, the four Hilbert spaces here, the four Hilbert spaces here. Or if you want, in this language here, here you have for each link two indices, which you can naturally associate to the surface, to the source of this link, and to the target of this link. The link is oriented. Okay, and this is a node, so you can rewrite this as HL, JL, and then for each node you have an index M, four indices, M1, M4, all associated with this node N, corresponding to these four links here. Or in other words, in this language here, I'm doing things, two languages in parallel, hoping this is more clear. I can rewrite this, instead of a product of the link, a product over nodes of HJL1, four of them, HJL4, where this L1, L4 are the four links coming out from this node. I'm just juggling so far. Why I'm juggling like that? Because I don't want a basis here, I want a basis here. So I've found a basis here, now I want a basis of gauge invariant things. So out of this basis, let's construct gauge invariant things. Okay? Invariant under which transformation? Under this SU2 transformation of the nodes. So let's consider how do this gauge transformation act. I have, say, one gauge transformation on this node here. It only acts on these 4 links, and it only adds on the index. Say these are all oriented outgoing, all on the source link, on the first one. So in other words, a gauge transformation on this a given node M acts only on these 4 vector spaces, these 4 Hilbert spaces associated to this the 4 links coming out of it. So this is H gamma tilde. Immediately I can say that H gamma without a tilde is the sum over JL, the product over N, not of this, but of the invariant part of this. The invariant part of HJ1, J4, which is the object that we called the intertwiner space between these 4 Hilbert spaces. So, since you were having hard difficulty in digesting intertwiners, let me do it in the other language, so it becomes clearer. So we have this basis here, and so we have this basis element here, JL, and for each node we have 4 indices, M1, M4. Just let me write this, which is associated to the node. And we want to write a state. So this is a state. These are all states in H tilde gamma. We want to write gauge invariant states out of that. But gauge invariant states are just a subset of that, a subset here. So a linear combination of those. So let me write them, and then I'll name them in a moment. So I want a linear combination of the sum of these indices, M1, M4, all of them, with some coefficients. Let me call I M1, M4 with 4 indices, JL M1, M4, N, and N. And I want coefficients for each node. So node 1, node N, and here M1, M4. These are node 1. These are node N. So I've just some linear combinations. Now this state here is going to be gauge invariant if, when I transform that acting, rotating on the indices, this is invariant. So if this is invariant. So if and only if this object here satisfy I M1, M4 rotation matrices H, each one lives in a different representation, J1, J4, M1, M4, N1, N4 equal I N1, N4. Sorry for bringing the indices up and down. So if these are objects with 4 indices in 4 different representations satisfying this, the state is gauge invariant. And if I want a basis of gauge invariant things, I want for each node to list an independent set of these such that any other can be written as a linear combination of it. So in other words, I want a basis in the intertwiner space. Okay? And I told you how to write a basis in the intertwiner space, because the simplest possibility of writing M1, M4 gauge invariant is to use the three-dimensional intertwiners, which are unique. I M1, M2, M, I M, M3, M4, M prime, and contract then GM, M prime. And the only choice here I have is to in which representation these indices M and prime live. So let's say this is a representation K. So I have J1, J2, J3, J4. This is a representation K. And how many of these independent I can write? As many as possible representation I can put it here. I have the Clebsch-Gordon condition that tells me what are the possible value here. Right? It's standard angular momentum composition. For instance, if I have 1/2, 1/2, here I can have either 0 or 1. It's only 2. And if 1/2, 1/2, only 0 and 1, so I have 2 possibilities. If I have 1/2, 1/2, 1, 0, then 0 is not allowed because 0, 0, 1, it doesn't satisfy the Mandelstam identity, but 1 is allowed because 1, 1, 0 does. So I have only 1. So on. Okay? Which means that I can label a basis of this intertwiners here with this basis, for instance, with this basis K. K, now let me call this K, and choose a basis here labeled by J, N, and K associated to a node, where I put the K object of node 1, the K object of node N. So I've constructed for you explicitly a basis in this space here, in H gamma, in the physical hyperspace. And the quantum numbers are 2, are a spin associated to a link, and some intertwiner, an element of a basis in the intertwiner space associated to a node. Of course, I can choose different bases here. I've just told you one possibility of choosing a basis in the intertwiner space. We're going to soon look for others. All right, well, I've just written a basis, so what? I mean, I promised you to solve a quantum mechanical eigenvalue equation, not to juggle with indices. Well, this is the basis I wanted. Why? Let's go to the operators we have. So let's look at the first operator, AL. So what is this? A square L is this. And we already looked at this object in when we just had one SU2 is a Casimir, right? And so this is just the Casimir, and remember that it has a property that it's diagonal in the Peter Weil decomposition. So, and it has a value in each representation, and in each representation J, its value is JJ plus 1. Okay, so L square acting on the states I have constructed, JL, how do I call KN, gives JL. So this is one particular link. It reads the value of that particular link, JL plus 1, times the state itself. Now remember that what we wanted to call the area operator in the geometrical interpretation is not just that, but is h bar g with some real number here, which I haven't specified. So let me just put the h bar g here and some real number, which I haven't specified, h bar g. Sorry, h bar g, so h bar g is square. So this is square. So the area itself, which is the square root of that, of associate, let me think about the triangle here. JLKN is some number, h bar g, square root of JL plus 1, JLKL. So I've solved the eigenvalue equation for the area operator. Explicitly, I have the eigenvectors, the eigenvalue. The area operator is completely blind to intertwiners. It doesn't see the intertwiner space. It transforms it into itself. It sees the spin associated to the links, and its eigenvalue is this number here. Let's look at the volume. What happens with the volume? And then we discuss the physical meaning of that, which is subtle, is not obvious. Yes?
This JLJ plus 1, it's not obvious in the board. Is it just something that comes out when you do the full calculation? I don't see where I can't see on the board where it comes from.
Because I referred to what we're doing the other one. This is the Casimir. I think this is exactly the algebra of the angular momentum.
Okay. Yeah.
So this is the total angular momentum in the representation J.
Okay.
So just look at your quantum mechanics book on the chapter angular momentum. There's a explicit computation of that, and it gives J plus 1. Okay. So on the representation J, the Casimir is diagonal, and it has value J plus 1. Okay. I don't have time for a good discussion of the volume, so let's postpone the discussion of the volume next hour. Let's say something about this here. It's already crucial. The point here is the following. J here has half integers, the JL, 0, 1 half, 1, etc. So this is a discrete spectrum. So the possible values of the area make some spectrum, standard spectrum. Which means, in particular, that you cannot have an arbitrary small area, right? So if this quantum theory is correct, it means that the area of a phase cannot be arbitrarily small. But wait a moment. I said at the beginning that we can take a portion of three-dimensional space, approximate it with big tetrahedra, and describe the quantum behavior of this geometry with these operators. But we can choose a smaller triangulation and do the same. So classically, I may think I can go this arbitrarily small, and I can approximate arbitrarily well any discrete and any continuous geometry with tetrahedra which are arbitrarily small. But tetrahedra arbitrarily small have an arbitrarily small area of phases. Quantum theory is telling no, you cannot. We have to stop at some point. There is a bottom bottom level at which you have to stop, which is of the order of h bar g. This is in centimeters 10 to the minus 66 centimeters, h bar g. So it's very small. It's a Planck length square, centimeter square, 10 to the minus 6 centimeters square. This Planck, L Planck square. So the theory is saying that whatever quantum state you build, you cannot approximate a geometry which is at a scale smaller than this one. Yes?
Just for curiosity, why is this always expressed in centimeters and not in meters?
Sorry?
Just by curiosity, why is this always expressed in centimeters and not in meters?
Oh, because the English are winning over the French. No reason.
Because of the imperial system?
Um,
We're going to do imperial with that inches,
Yeah.
the English are also losing. Is what is MKS and CGS? They're two common systems, and I don't know why the physicists, theoretical physicists, like centimeters, seconds, grams better than meters, kilogram. There's no reason whatsoever. Zero. No meaning whatsoever. If you want meters, I can add four. It's better meters, right? Because it's minus 70. It's easy to remember. So this is a minus 70 meters square. So it means in a meter square, there are 10 to the 70 quanta of area. Okay? So the statement here is that if you believe the theory, when you measure an area, you can never measure anything smaller than that. That's the bottom line. So this is the first quantum effect we're finding. It's not the only one. I think there's going to be more, and in a sense more interesting. But the area of the minimal element of geometry which we can think cannot be smaller than this quantity here. And this comes out not as an hypothesis, not as a statement a priori, but as a standard eigenvalue calculation if one takes this Hilbert space and these operators as a description of quantum geometry. So we have a description of quantum geometry, more or less following a standard description of quantum systems in which you replace variables with operators with a Hilbert space, and we have immediately a result about discreteness of geometry in the small. Now, discreteness of geometry in the small is not a accidental, funny feature of quantum gravity that like a curiosity, because continuity of geometry in the small is what leads to ultraviolet divergences in quantum field theory. So if there is something cutting off the continuity of geometry at small scale, immediately you have a hint that ultraviolet divergences in quantum field theory come from disregarding this fact about nature. Right? So it's of substance, that. Good. So I want to stop here, and next lecture is about the volume, and you'll see there's a lot more physics that comes out thinking about the volume and area and volume together. Good. Thanks. Stop.